And then before I forget, the first thing I want to do is to talk about the solution of the previous homework assignment, the one about the flags when you're adding numbers. So we'll deal with that one first. The one with subtraction is due tonight at 9:50, which is the end of the lab after the class. Okay. So you still got some time, if you figure out how to do it, you can just go ahead and do it. But some of you probably can do it during the class, because you have your computer with you. Okay. So we'll go ahead and get started with that particular one. And I'm going to just use a text editor here to give you the examples. This is with addition, okay? All right. Let me create a folder first for what we'll be capturing today, so we have a folder to keep everything. 319. And by the way, I created a new ISO, a live ISO image. This one does work with NVIDIA. I found out what the problem was. It's one of those things where there are multiple sources for the GLX driver, and NVIDIA was one of those, but it wasn't the highest priority one. So the installer decided to do a symlink to the wrong one instead of the NVIDIA driver. That issue is now resolved. So if you download deblive.iso again, this time it will work on computers with the NVIDIA chipset. Okay, so let's go ahead and get started with the homework assignment, the previous homework assignment, the one that was due last week, which is about addition. Now the way I look at this one is I would try to limit my possibilities by using the overflow and the sign flag, because those two combined are very, very useful. So let's go ahead and take a look at the overflow flag for addition. So this is for addition, not for subtraction, but you can apply pretty much the same trick to subtraction, except the definition is a little bit different. Can someone remind me what is the overflow flag, or what is the equation defining the state of the overflow flag? And I would just use the symbols that we used before. I'll use A3, or let's see here. A is the most significant bit of the first operand. In addition, it doesn't really matter because the operation is commutative. All right, so A and B are the most significant bits because that's the only part that matters. And C is the most significant bit of the sum, okay? The overflow flag is defined to be a logical equation of these three different bits, okay? And the way it is defined is it is a disjunction between two. The first one is A and B and not C. What this part is representing is the first number is negative, the second number is negative, but the sum is non-negative. That's basically what this is representing. Because when A is true, it means A is a 1. But when A is a 1, which means the most significant bit of the first operand is a 1, it means it is representing a negative value when interpreted signed. The same thing goes with the second operand. When B is true, quote unquote true, or when it is 1, it means the most significant bit of the second operand is representing a negative value. When not C is true, it means C is false. C being false means it is 0. So that means the most significant bit of the sum is a 0, which means it is non-negative. Adding two negative values giving you a non-negative value means the sign of the result that does not make any sense, and as a result, the O flag or the overflow flag is set. The flip side of this is also true. Not A and not B and C would represent adding two non-negative values and end up with a negative value, in which case the sign also does not make any sense. Okay? Now this is particularly important because if the O flag is true, it tells you that it has to be one of these two cases. If the O flag is cleared, it means this cannot be true. So that points you to the other two possibilities. What is the sign flag in this case? The sign flag in this case is simply C because it is the most significant bit of the sum. So that's why the sign and the overflow flags are particularly useful, because it gives us their combination will help us limit the possibilities. Okay. So having defined this, we also want to define the carry flag. The carry flag, if you just look at A, B, and C, C is not even important in this case, but you can see that when A is true and B is true, the carry flag is definitely set. In other words, if you look at the entire definition of the carry flag for addition, it is this thing or something else. Okay. That's something else. We can deal with it later. But we know for sure that when A is a 1, B is a 1, the carry flag has to be clear. Has to be set. Okay, so that gives you a useful idea too. The Z flag in this case is the negation of C and C or blah 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 blah. Okay. So once again, it is very important. I have C for both the carry flag and also the most significant bit of the sum. I'll change one to a different number, to a different letter. So I'll call this R for result. Okay. And there you go. 2 more? All right. There you go. There we go. Okay. Now that is important, because if you look at this flag here, the sign flag is nothing more than just the most significant bit of the sum itself. The Z flag, on the other hand, is the negation of a disjunction involving the most significant bit of the sum. Okay, so you have to ask yourself this question. When the sign flag is a 1, is it possible that this expression will give you a 1 as well? It is not possible. I don't even care what the other stuff is, because as long as R is a 1, the negation, as long as R is a 1, the disjunction involving R is going to be a 1 as well. But the negation of a 1 is going to be a 0. So that means when the sign is a 1, Z has to be a 0. Is that okay? It's intuitive too, okay? Because the sign flag is the most significant bit of the sum, and it is a part of the result. And so that's why this makes sense. Now this right away will rule out 4 possibilities. Okay, so let's go ahead and spell out the 4 possibilities. We have C, Z, S, O. Is that how it's ordered?
C, O, S, Z.
C, O, S, Z. Okay, so we'll keep the same ordering here. And the 16 possibilities are as such. Okay, we can just list the binary numbers. Just add it up to 15. And then I'm getting a little bit tired of this, so I just do copy and paste, change. There you go. So all 16 possibilities. Are we doing okay so far? Okay. So we know the combination of sign and Z being both 1s are impossible. So let's locate those, because we can use that one explanation right away on those. So those are these 2. So we can explain this one. The sign and the Z are, so we'll see note 1. Okay. So everything that has these 2 bit set, we'll just say note 1, and there should be 4 of these. Note 1, and the same thing here. Note 1. So note 1 will basically say sign is 1 if and only if R is 1. But if R is 1, then R or blah 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 is also 1. Not R or blah 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 has to be a 0. And that's it. Because it leads to contradiction. Are we doing okay so far about the explanation of note 1, why those 4 particular combinations are impossible? And I'm just picking the easiest way to explain these 4. I mean, that really is the easiest one to rule out. Any questions about this part? No questions? All right. Let's take a look at this one here. Can someone give me a combination that can give me basically no flag will be set? This one's easy. 1 plus 1, 1 plus 0, 0 plus 1. You know, there's a whole bunch of combinations here. So 1 plus 1 will serve this purpose. What about the case when only the Z flag is turned on and none of the other flags are turned on? 0 plus 0. Yep, that's the only one that can do this one. Okay, this one has a whole bunch of combinations. Okay, you know, and etc. What about the case where the sign flag is a 1 after the result and everything else is cleared? That's pretty easy too. -1 plus -1. -1 plus 0 would do it. Okay. And there's a whole bunch of other combinations that would do it. What about this one here? Only the overflow flag is a 1, the sign flag is a 0, and everything else are zeros as well. Well, let's take a closer look. Okay, this one does take a little bit more thinking, and we don't know right away. It's not obvious. Okay, we cannot just say, oh, it's obvious. This combination will do it. It's not even obvious whether it is possible or not. Okay, so we'll say note 2 here, and at note 2 we'll say, okay, this is about O is 1 and sign is 0. Okay, now whenever O is 1. It really helps to narrow down the combinations already, because O can only be a 1 when this entire expression is a 1. Now, if we also have sign equals to 0 here, that means we have restricted ourselves to only this particular expression being true. Are we still doing okay so far? Okay. So with this combination being true, it means the most significant bit of the first number has to be a 1. And the most significant bit of the second number also has to be a 1. Does it make sense? Now, what does that also guarantee? It is right, well, it's not right next to it, but it's close. The carry. The carry has to be a 1 in this case. So that means this combination is not possible, because whenever you have O being 1, sign being 0, then the carry is guaranteed to be a 1. Okay? So we can use that explanation. So note 2 is over here. Note 2. Okay. So this means out of the expression, we know that A and B and not R is 1. And that implies A and B are both 1s. But that also implies C equals to 1, which is not what this combination is trying to get. Okay? There is one more combination that can use exactly the same explanation, which is O equals 1, S equals 0, and C equals 1. Okay? Because whether the 0 flag is a 0 or 1 doesn't really matter in order to apply this particular explanation. So when we look at this combination here, the one right next to it can also use exactly the same explanation. Is that part making any sense? So as soon as I find a combination that does not make any sense, I'm trying to find the same pattern elsewhere and say, oh, I can apply the same I can apply the same reasoning and explain why the other combination is not possible. So this way, I'm knocking out all the impossible cases relatively quickly and only be left with the ones that are possible. What about this one? This one says the overflow is a 1, the sign flag is a 1, the 0 flag is a 0, and the carry flag is a 0. That seems possible to me. Okay. We are dealing with addition. The sign flag being a 1 means I'm adding 2 non-negative values ending up with a quote-unquote negative value, and it cannot be 0. Well, that's pretty easy. You just have to add these two numbers, and the result is 0x80, and that would generate this particular flag combination. And these are hexadecimal. Does anyone want me to look at this as a binary number, or is that okay just remaining as hexadecimal? preferences. This is okay. All right. And obviously, this one has a lot of other combinations that will work as well. All right, let's take a look at this one. The carry flag is set, but everything else is cleared. Is that possible? Okay, let's take a look. If the carry flag is set, there are two ways to make it, to make the carry flag set. The first one is A and B both being ones, okay, and then the other one is to use bit 6, have the bit 6 carry to go over and bump this one over. All right, so let's take a look at a particular combination, and you can tell me whether this works or not. What about 0xFF, which is 11111111, plus 0x plus 2? Okay, 2 is just 2, doesn't matter whether it's base 16 or not. Do you think this will do the trick? It will do the trick. Okay, this one will do the trick because the result of this is actually just 1 itself, but the carry is going to be set. Are we still doing okay? What about this one? If the other one is possible, how about this one? That will do it. And this one is a little bit more tricky because once again we have a kind of strange combination. We have the carry flag being set, the sign flag being set, but the overflow is cleared and the 0 flag is cleared. Is that possible? Okay.
FF plus another. FF plus something bigger like FB.
Okay. What is the result here? As an 8-bit addition, what is 0xFF plus 0xFF?
FE.
Is FE, exactly. Okay, so let's take a look, when this happens, does it explain, why the carry flag is going to be a 1? Yes, because the most significant bit is set, the most significant bit is set, and as a result, the carry flag is automatically set in this case. What about the sign flag? The most significant bit is set as well. What about the overflow flag? Why is it a 0? Why are we not overflowing?
Because the signs make sense.
The sign makes sense. We're adding a non-negative value to a non-negative, excuse me, the other way around. We're adding a negative value to a negative value, ending up with a negative value. Makes perfect sense. And obviously this is also not 0, so it's fine. This one we explained already, so we can move on. And once again, we have the overflow flag being a 1, the sign flag being a 0. So we want to see whether this combination is possible or not. Now, if you want to find a combination to make this work, it really helps to narrow down the possibilities. So I'll go to note 3 here. And note 3 has to create this combination. Here's note 3. Note 3 is going to utilize O being 1 and sign being 0 as a clue, which means we can use a good portion of what we had already. Okay, because all of that stuff is still implied. Whenever overflow is a 1 and sign is a 0, all of that stuff is still true. And in this case, is the carry flag a 1? Yep, the carry flag is a 1. But the sign flag is a, oops, okay, take it back. The sign flag, the 0 flag is a 0. Okay. Now it is entirely possible. Okay. But this really helps us, narrow down, to, the exact combination, because when you look at the numbers, we are basically looking at 1 blah 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 plus 1 blah 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 blah. Ending up, I don't even care what this row looks like, so we can just put a 0 here because we know for sure that's going to be a 0. And we end up with a carry flag here, and we end up with something else here. And we also know the result is going to have a, let's see, the 0 flag is a 0. The 0 flag is a 0, so this part here can have a 1 or not. but the sign flag is cleared, so that means this has to be a 0. Now, if you see that this is a 0 and this is a 0, that automatically means this has to be a 0 as well. But the rest of it, at least one of these bits has to be a 1. So I have, this portion, kind of filled in. Can you figure out, what the other, what the dots may be? Now, if this is, too much, if this is like, oh, there are too many, unknowns, you can always make it smaller, okay? Because, we really don't need, 4 bits to make the case. 2 bits is already enough. All right. So if I turn it into something like this, can we find a combination to make this happen? Okay, there's one more thing that we already know. We already know this is a 0. There are no carries from the prior digit. So to make this a 1, that means this has to be a 1, right? Now to make that a 1, that means out of these two, one has to be a 1 and one has to be a 0. It doesn't matter which one is a 1 and which one is a 0. I can just make it like this. Does that make sense? So this is how I would approach the problem. Is I use some of the flags to help me kind of narrow down the possibilities, and then I just work my way back up, to say, okay, this is what we want to end up with. But according to the equations of the flags and also the bits, we are going to we're restricting what can possibly be those other what can those other bits possibly be. Right. But this is a 2-bit number. Can we extend this to an 8-bit number so it will fit into the question itself? Just pad zeros on the right-hand side. Okay. All right. So that's note 3. Note 3 is possible, and just to make it complete, I'll give you the example, which is FF. Let's see. If I use this one and just use pad zeros on the other side, I would not have F here. I would have a C 0 plus, that would be an 8 0 equals to 4 0. There we go. Is that okay? I just did all the 0 padding on the right-hand side and converting the binary number to hexadecimal, combining all of those in one step. Any questions? What if someone says, but I'm really not good at converting these numbers to base 8 and base 16 and then extending it by padding zeros on the right hand side. Which operator in C or C++ can be helpful for this kind of thing?
Shift left, shift right.
Yep, the shift operation. In this case, which way are we shifting? If I give you the 1 1, the 1 0, and I want to pad zeros on the right hand side, will be left shifting, exactly. And GDB has the left shift operator defined already. Okay. Very good. How about this one? This one is almost the same, except I want a 0 at the end. In other words, I want this to be a 0. That's the only difference from the previous case. Would that be possible? Yep. Because if this is okay, let me just copy and paste it so we preserve the other one. Okay. If I want this to be a 0, that means, and this is already a 0 to begin with. Okay, this has to be a 0. I need this one to also be a 0. But for this one to be a 0, I also need this one to be a 0. But I also need everything else to be zeros, because if I have a 1 somewhere else, the result is going to be non-zero. But that's pretty easy. If I pad zeros on the right-hand side, everything else is guaranteed to be zeros too. So in this case, we are going to apply the same technique. We just pad 6 zeros on the right-hand side to all the numbers, and then we end up with 0x80 plus 0x80, getting a 0 at the bottom here. So moving back to here, the example is 0x80 plus 0x80 equals 0x00. All right. One more combination and we're all done. We're down to this one. So when you look at the flag combinations, This one is saying that we have overflow, sign, and also the carry flag all set at the same time. The Z flag is being a 0, but that part is easy to deal with, so we are not really too concerned about the Z flag here. Okay, so is that even possible? Well, we'll pull that out to node 4 in this case and figure out why it is not possible. Okay. So node 4 goes here. In this case, we have O equals 1 and sign equals to 1 as well. Now that automatically means out of the equation for the overflow flag, not A and not B and R has to be a 1. Because the sign flag is R, and that's the only side that will make it true. Okay. Now if that is a 1, then we know the addition is going to look like this. Okay, just looking at the most significant 2 bits, it's going to look like this. We know that it starts with a 0 for both numbers because they have the most significant bits being zeros in both cases. So we know we have 0 plus 0 blah something, and because of that, we know this one has to be a 0. Okay. The carry flag is a 1, so we want this one to be a 1. I think we're done already. There's no way to generate this one here when 0 plus 0 cannot generate a carry, and neither can 0 plus anything. The only time you can have a carry is when you have 1 plus 1. But we have already ruled out both possibilities of 1 plus 1 here. Okay? And you can just explain that using this particular terminology, just saying that A has to be a 0, B has to be a 0. So A plus B has to be a 0 as well. But when that thing is added to the carry from bit 6, that also cannot generate a carry guaranteed. And as a result, it is not possible to have all those 3 flags being on at the same time. Okay. So I will just go ahead and finish everything. So right here we can stop because we can say, going back to here, but that means A plus B has to be a 0. Okay. Not generating a carry of 1. The sum, okay, the sum of A plus B and the carry from bit 6 cannot generate a carry either because one of them is a 0. So we just blew both chances to have a carry of 1, and as a result, we cannot have a carry of 1 in this case. All right. So are there any questions about the solution to the add flag homework assignment? Yep, go ahead.
Bar descriptions aren't that accurate.
As long as it is still fairly reasonable, and not just I could not find a case, or I enumerated all possible cases and this still won't come. This particular combination is still not observed. It has to be something that's using the definitions of the flags. Now you don't have to use the bitwise operation. You can use the signed and versus unsigned interpretations. As long as it is explained. Since I haven't seen yours, I cannot tell. I cannot say whether it will be okay or not. Okay. But is this part okay? Does everybody understand the explanation? Okay. So you can apply some of the same techniques to subtraction. Now with subtraction, the definition of the overflow flag is different. Okay, this equation is no longer like this, but you can still use it to help you narrow down cases. Okay, and you can still use the same approach and say, oh, when would the carry flag be turned on? Well, in this case, in the subtraction case, 0 minus 1 is the only time when the carry flag or the borrow flag is going to be a 1. So that will help you, using the same technique, that will also help you, locate and find out, okay, is it even possible? If it is, how do I generate the bit pattern to make that happen? All right. So are we doing okay so far? Okay. So I will save this file in case I need to refer to it, I'll save it into today's folder. But since it's, oh, wrong class. There we go. All right. With this out of the way, I'm going to continue with writing structured code in assembly. Okay, so we are already done with control structures. I think we covered everything in control structure. So today is basically just practicing what we have learned already, and just go step by step to transform the code from C code into assembly code. Did anyone do the brain teaser from last time? Remember there was a little problem that I left you guys with, and no? Okay, so you did it? Okay, so let's go ahead and do that part first. This is a related question. I never thought about it until now, and I just realized, hey, that question is related to what we are doing here. One of my cisp310 students is taking cisp310, which is Introduction to Computer Science. It's also one of the hardest class to teach. When you're talking about flowcharts and stuff like that, it's really hard to keep the interest of the class when most students are not computer science students. The math majors, they are engineering majors, and they have no interest whatsoever in flowcharting. But anyway, the question was, how come I did not use, when I teach cisp300, how come I do not use flowcharts to represent the logic of a program? And instead, I just insist on using pseudocode. Conditional statements, loops, are the two main control structures. I don't even bother to use flowcharts, the diamonds and wires, lines going everywhere. Can anyone kind of guess why I do not use flowcharts?
There's chaos.
But why is that? I think you're on the right track.
Because I had to do them for my 300 ones.
Given any flowcharts, okay?
Yeah, there's so many different interpretations that it's.
Well, the interpretation is not the problem. Okay, when you look at a flowchart, every symbol is well defined, especially the diamonds, which are the branches, right? So let's say this entire thing here is a flowchart, and I'm just picking two particular lines here. Okay, this is out. It's the trash can. Trash can is all the way over there, too far. Okay, so this one is aligned somewhere, and the flow of logic is going down like this, and there's one other line, where the flow of logic is going up. So this is a really complex, flow chart already, okay? And I'm just picking two random places and say, you know what, my business logic decides that sometimes I need to go from here to here. With a flow chart, it's easy to capture that concept, right? If it's true, go here. If it's false, go here and merge with that branch. It's very easy to do with a flowchart. But how about translating this program into C or any structured programming language?
I went the other way. I wrote the code and then I went back to the code.
Well, to truly implement this, you'll be relying on if whatever the condition is here.
Code 2.
Right? That doesn't make your program structured at all. And remember, and think about doing this 20 times. Okay? So flow charting actually, I think, encourages non-structured thinking, which makes any logic coming out of this entire process, a programmer can look at it and go like, I cannot do this. Is everybody getting that point? Okay? And that's why when I teach cisp300, I don't use flowcharts. I use the picture only when I'm explaining the basic concept of what is a conditional statement. It's a branch, okay? You come in here, you can choose one of the two paths, you execute whatever is on one of the paths, and then they merge together, and then you continue with whatever statement is after that. Same thing with loops, okay? But it's only when I'm explaining those particular constructs that I use a flowchart just for visualization. But after that, I don't refer to flowcharts whatsoever again. All right. But people look at this and go like, but isn't that the only tool we have in assembly language programming? We don't have conditional statements. There's no else. We don't have loops in assembly language programming either. We don't have loop when there is a loop instruction, but it doesn't do what you think it's supposed to do. So we are really only left with mechanisms like this. Now that tells you one thing. You don't want to think in assembly language when you're writing programs. Does everybody understand what I'm saying? Okay, I'll say that one more time. You don't want to think in assembly language. Even in this class, you don't want to, when you're writing your programs, do not think programming in assembly language, because you will end up with stuff like this if you did that. So how do we write programs in assembly language?
C.
You start with C, exactly. You start with a high-level programming language that is structured, and then you go through the process that we talked about on Thursday to break it down into pieces that looks like this. But they are not random. They're not only there because, oh, I think we should have it there. No, it's because of a very mechanical process to put it there. Okay, are we doing okay so far in terms of the concepts? Okay. So let's go back to the text file that we have on the other day, and then we'll go ahead and translate that step by step. So that's okay, open. It's here. Okay, so this is the program that we want to translate. Did we actually do it or not? I think this one was a brain teaser.
I said taking out the
Okay. All right, so we'll do this. And is my other text window still open? Yep. Nope. It closed my other one. Well, since they're all text.txt. Oh, there we go. No. I have to actually go back to that folder. Reopen this. There we go. All right. This is what we want to. This is what we want to do in assembly, and we'll just go ahead and focus on how are we going to do it. Now, before we proceed, we kind of have to explain what X and Y are, because otherwise we cannot pick the correct instructions to do this. So we have to make certain assumptions here. So we can say assume X and Y are, do you want these to be signed or unsigned? It doesn't matter to me one way or another.
unsigned.
You want it, well, we can start with unsigned, okay? So they're unsigned. Do you want 16-bit or 32-bit numbers? 32-bit, okay. Okay. We can make these signed 8-bit numbers. It really doesn't matter all that much, okay? Okay, so we are going to translate this program step by step. And for those of you who took my cisp310, this approach should look kind of familiar, because we're just doing it revision by revision, line by line, step by step. There we go. So we'll go ahead and translate one line at a time. If I'm translating this line, I will comment it out, just to remember that this line is now translated. Can we translate, initializing variable x to a 0 using only one instruction in assembly?
No.
Now we have to remember to indicate the width of the operation. Now that we know it is a 32-bit number, which letter should we use here?
L.
L, okay. And immediate 0 to x. That's all. Okay. In other words, I'm assuming that x is defined like this. So x colon dot in 0, y colon dot in 0. That's how they were defined or allocated. Okay. So what about the next instruction? For the next line? Same deal. That is pretty easy to do. Okay. We'll call this the first revision. In other words, I'm not greedy. I'm only testing or implementing a few things, for each time, for each round. I can test the program. As far as I can translate at this point, I have to comment out all the other C code, but I can actually make this program assemble and then go to a particular label, examine the values of x and y. I mean, obviously, in this case, it has to work, but I can actually test the program step by step. I don't have to translate the entire program and then test it. Okay, so let's go ahead and try to implement the loop here, okay? So I'm going to copy and paste pretty much the entire code here, except I'm only translating a certain part of it. This time I'm translating the structure of the loop itself. The content of the loop I can remain in C, at least for the time being. To translate a loop, you have to go back to my notes. Okay, so if you go back to my notes here, and this one, I never remember which one is the one. Okay, this is the correct one. So we go to the pre-checking loop here. Whenever we see, C code that looks like this, we'll translate it into a template that looks like this. Okay, well that's not too hard. In other words, we have to define a label for the beginning of the loop. Now I use L1 and L2 when we are only looking at the translation, the template. But in reality, it really helps to not use L1 and L2. Instead you can use loop begin as a label, because now the label, the name of the label actually has a meaning. Okay, it marks the beginning of a loop. So instead of doing this, we can say loop begin or begin loop. You can choose however you want to name those. And this one is loop exit. Okay, it's not loop end, but loop exit, because it marks the exit point of a loop. Okay, and inside, we know that we have, we need something like this here. We need to go back to L1. Now this one I'll just go straight to assembly, because go to L1 is the same as jump to L1, except in this case it's not L1, it's loop begin. And then we have to deal with the condition. So let's say that we don't want to deal with it right away, so we just say in pseudocode or in pseudo-C, we say if that is not the case, okay, if it is not x is less than 3, we want to go to the label called loop exit. Okay, so we have a little mixture of C and assembly code in this case. And we just call this revision 2, and then we go to revision 3. In revision 3, we look at this statement here and go, is there a better way to say this? You can always say if x is greater than or equal to 3, go to loop exit and take out the negation on the outside. Okay, so we'll go ahead and do that. Comment it out and say, well, we can express the same thing, exactly the same thing, like this. If x is greater than or equal to 3, go to loop exit. Okay. I'm introducing yet another revision just for this, but you don't have to go for all these baby steps. Okay, this is revision 4. In revision 4, we look at this statement here and go, hey, it looks like this is close enough to what we can do in assembly. Let's try to do it in assembly code without any further translation. In fact, there's no way to translate it into any lower level C construct at this point, because we have boiled everything down to a conditional branch and a simple comparison using 2 numbers. Okay, there's no expression to compare anymore. All right, so we'll try to translate this into assembly. Okay, and if you remember from last time, this kind of thing would look like a CMP, in this case CMPL, because we're comparing 30-bit numbers. So we'll just go ahead and do some placeholders, and we'll come back and figure out what those placeholders should be, how they should be filled in. And we have a conditional branch here, jump based on some flag to, well, we already know what is the label to exit to or to jump to. It's loop exit. All right. So now the question is, how do we translate something that looks like this in C into something that looks like this in assembly? And the key is to read the code in a particular way. Okay. We know we have to compare x and 3. The question now is, which one is our first operand and which one is our second operand? Compare is subtraction of it will subtract the first operand from the second operand. So that means 3 has to go here and x has to go here. And how do we figure this one out? Remember last time, I kind of have a particular way of reading this. This code or this combination of code here is saying jump to loop exit if and only if x relates to 3 in a particular way. And that particular way is just greater than or equal to. So what do we specify here to mean greater than or equal to? Do you remember which way we chose to interpret x and y? It was unsigned. Okay? If it's unsigned and we want to express greater than or equal to, what do we use?
Either 0 or G.
No, G is signed. G and L are signed. A and B are unsigned. Okay? But we are looking for greater than or equal to, and the quickest way to do it is to say not below. Right? Not less than is the same as greater than or equal to. So that means that J and B will serve that trick. Good. Let's stop here, and then we'll take a look at this code and see whether it makes sense. So I'll read it again and see whether it makes sense or not. This tells me that we want to jump to loop exit if and only if x is not below 3. X is not below 3 is x is greater than or equal to 3, which is exactly what the original C code is specifying. Are we doing okay so far? So that should work. And then we go through even more iterations. All right, so now the rest of this is pretty easy, okay? Because we just have this part left. Y gets y plus x. Ideally speaking, if we want to do something that looks like this. Add L, x, y. Because remember, in our assembly code, the second operand is the destination. And in the C code, the destination is the left-hand side. So we want y to be our destination. So this add L instruction, in theory, would do the trick for us. But it doesn't. Okay, it doesn't work. Because in this case, x is a direct operand, which is a memory operand. Y is a direct operand, which is also a memory operand. In every instruction in the i386 instruction set, you can only have up to one memory operand. So we cannot do this, okay? Even though this would be the quickest way to do it, we cannot do it this way. Well, if we cannot do it this way, we can always introduce or use up one register for this purpose. So we just use a register as a temporary place to put the value that we are copying. And that would do the trick. Then we can do the same. Well, the next one is easy. The next one, just adding 1 to x, is just adding $1 immediate to x. And we have the entire code translated. Are we doing okay so far? Okay.
Didn't we need to put the original value of y into EAX?
Put the original value of y into EAX.
No,
It's
he's adding x to EAX and then
Oh.
adding EAX to y.
Yeah,
Yeah,
so it's
okay, I
EAX
made a
before we
mistake here.
begin.
It's move L, not add L. Sorry. Thank you. All right. So, how do you check your code and make sure that it is behaving the same way as your C code? GDB it, right? We're making GDB a verb in this class. GDB it. All right. Do you guys want me to do it, or do you think this will do the trick and don't want to waste the time to do it?
Why not?
You want to do it? Okay.
Why not?
Why not? Now, if you look at all these revisions, if you do a compare, like a diff between the revisions, you will clearly see, what I changed, from one revision to the next. There are different tools to do that. Does anyone want to know how to use a diff tool? Because it's a useful tool. It's a useful skill to learn. Okay, not only for this class, but also for your other classes. I'll just show you what it is, and then you guys can say, I don't need that, or this is kind of a neat trick. So we'll pick 2 revisions that are close, but not exactly the same. Maybe this one and the next. Okay, revision 2 and revision 3. I'll create those files first. Okay, so block copy here, and we'll go ahead and use another editor. I don't have gvin, but I do. There we go. And first. Oh, okay. So go to this folder. I'll just call this revision 2 dot lowercase s. And then we'll pick up the other one. Paste it here. And save it as revision 3. Save revision 3.s.
You've got revision 3 at the beginning of that uncommented.
Sorry?
You've got revision 3 at the beginning of that uncommented.
Yeah, that's fine. It doesn't change what I want to demonstrate. I mean, it really is still okay. All right, so we're dropping down to the CLI or the command line interface. Go to the folder where the files are located. I don't have to do it, but it's just more convenient that way because otherwise I have to specify the subfolder name. Okay, so we have revision 2 and revision 3. There are different tools to do it. The most traditional tool to do it is a command called diff. Okay, diff is an extremely useful utility program because it gives people the ability to find out how source code has changed and create patches for the source code. Okay, but in this case, I don't want to use diff because let me show you the output of diff without any options. So I can say diff revision2.s revision 3.s. And it shows me the differences, okay? Using the greater than symbol to mean, this file has this, and then using the less than symbol to mean the other file has that. It's not really intuitive. All the information is there, okay? But it's not intuitive. What is intuitive is to do it like this. You can say vim diff, okay? Vim diff is combining Vim, which is a visual editor, and the diff utility program. And then you can just give it any two file name. In this case, it's revision2.s, revision3.s, just like that. And then press the Enter key, and it is highlighted. Burgundy lines, not burgundy, but purple lines. The purple lines represent something is changed on that line. Okay. The blue line indicates something is added. So 2 new lines were added in revision 3 that were missing in revision 2. But on that one line, that has the pound sign, that is purple, that line is changed from revision 2 to revision 3. So I think this is a pretty nifty tool because it just really helps you visualize, the changes that you have made. And the best part about this, I cannot save the file because otherwise it kind of messes up the whole thing. You probably cannot see, but this pound sign here is in red. It's not purple, but actually red because it is the character that is changed. Now, if I insert a pound here, well, it doesn't change it right away. I thought it would do that. That means some other changes are here. I thought it would undo the purple when the 2 files are the same. Apparently I was wrong. But nonetheless, this is still a useful tool. This is also a very crude way of keeping different revisions of your program, not only for this class, but also for your C, C++, data structure classes. Whenever a file or a program is partially working, you save it under a different name, or copy it to a different name to take a snapshot of the program.
Is there an nano diff?
A what?
Nano diff?
A nano diff? No. But there is a vim diff 3 that can compare like 3 files side to side, which is really helpful depending on what you're doing, because vim diff 3 is useful when you're trying to merge changes that is coming from an outside source. So this is a very crude and rudimentary way to do revision control. Okay, revision control is a very important topic. You probably have already experienced the convenience of revision control. For those of you who don't want to deal with it, it's definitely not required in a class like this. But for those of you who think, well, maybe I'll look into it, you can look into RCS. Okay, RCS intro is one of the topics. Oh, I guess not. RCS itself is installed. What about the intro part? that's not the RCS that I'm looking for either. I have get installed.
Oh, nice.
Yep, so get is installed. Now, I don't want to use get, because get is a kind of much more complicated than the other ones, but get also allows you to share projects with other people. How many people have used get up to this point? No? Okay. Can you describe it?
I don't like using it.
You don't like using it?
No, I usually use Team Foundation Server, as I usually program in a Windows environment.
Okay. Get is available for Windows as well, and it has GUI tools available too. So you don't really have to learn. Sorry?
It has meld.
Meld?
Meld works with Git,
Okay.
and it's like the Vim3 you're talking about.
Well, it's like that, but it's even more than that.
It's
because
way more than that.
It's way more than that. I can, yep, go ahead.
I was gonna say that when I used it, I was given a branch, and somebody above me handled the merging all the branches together when the time came.
Right. Or you can decide not to merge to the branch too. You have a choice whether to, to merge into the main branch or not. You can have your own changes remaining local all the time. You don't have to push your changes. I can give you one quick example that is really, really recent. I was making changes to the Moodle source code because there were things like for grading your exam one, I had to implement a new feature to facilitate the grading of your exam one, which reminds me I have the entire pile of exam one here. But then I have a problem because if I change the source code of Moodle and upstream they also have updates, then I have a problem because now what am I going to do with my changes when I am reinstalling the new version of Moodle? I have to re-implement all my changes. So instead of doing that, where I have to remember all my changes, I use get. Okay, I create a branch of my own, and it was tracking changes that I made to the Moodle source code. When it is time to integrate changes from upstream, which is the main branch of Moodle, the tool can automatically figure out, okay, this is the file coming from the upstream source, and it will make all the changes from upstream, but it will also remember, oh, you know what, Tech, I remember that you made that little change in this program. As long as my little change does not conflict with the upstream changes, it will automatically merge those changes, and I don't have to re-implement all my little changes to Moodle. Is that making any sense? So that's what get can do. I mean, get is not really just for a single person maintaining a program. It is a lot more useful, than just a single person maintaining a project. But it can also be applied to just one single person. Are there any questions about revision control tools? This is a typical revision control tool. It's the revision control tool at this point. No questions? What if you want to share a project with somebody and you don't want to run your own get server? Nobody knows this resource? GitHub, yep.
Wait, that was
Well, it's a useful
I
tool.
thought it was more.
No, it really is just that simple.
Oh, yeah, you just clone a project to your own repo.
Yep. So you just go to GitHub.
They have a lot of really awesome open source stuff here.
Yep. I think it's taking over SourceForge, because SourceForge was the open source, resource. If you want to host a project and have multiple people to contribute, that used to be the place to go. And I think most people are, putting their source code into GitHub instead of SourceForge. So this is a place where you can get, resources for free, so that you can manage a project, shared by different people. It's really helpful. If you're not interested in something like this, totally ignore that. On the other hand, if you think, hey, I want to try this one out and see if I can share a project with somebody else, this is a good starting point. All right. Any questions? What is the value of revision control, regardless of the mechanism?
Values.
Go ahead.
There's a lot of values. There's the ability to scroll back or bring back changes. Like if you want to try something new, but you don't want to overwrite an existing working project.
Mm-hmm.
You can try out your new things and throw out any work that doesn't work.
Mm-hmm.
Yeah, if you have a project that's working, you leave it on the master branch, and then you check out a branch from master, and you can make whatever changes you want. You can delete the whole thing and still have your master branch.
So in a way, it's a kind of fancy way to back up a project too, right? Because whatever you check into the repository is already saved. So if you check it out later on and make additional changes to it, those additional changes you can toss it away without affecting what you have already stored in the repository. It's also a good way to kind of manage changes because it allows you to visualize changes between revisions. How many people have the experience of getting a program to work up to a certain point, and then one day you make one change or two changes and the entire thing just blew up and stopped working altogether, and you had no idea, you could not remember what changes you made to the program.
Control Z.
You can make one tiny little change to a program, which at the time you do not think that it would be important, and it can break your entire program. Now, with revision control and the discipline to make use of the tool, okay, whenever your program is tested, okay, I know the program is not all done yet, it's not completely correct, but at least I can get it working up to this point, and you check it in, and then you comment your check-in, and you say, okay, this particular version of the program can work up to this point here, okay, and just describe it, okay? And then you make some silly changes to the program, it broke it completely, okay? So what you do is you just use the tool and you say, compare to the last time I check in and show me the differences. Then it will show you like, okay, you just made 3 changes, from that time, and one of these 3 changes has to explain why the program is now broken. So it's a really useful tool for that kind of thing, and it applies to not just assembly language programs, it also applies to any type of source code, including HTML source files, okay? PHP, HTML, C, C++, Java, anything that's text-based, it will work really well on.
The thing I like about it is keeping your program up to date. So like, if I do some stuff on the side at work, I can check that stuff in. When I get home, I can update my local files. So they're always up to date. And no matter what computer I use, I always have the latest and greatest. I don't have to worry about, oh, did I copy that file on my thumb drive? And it's just there.
I worked for a software company for the longest time before they had a revision controls program, and it was painful. There were only the 3 of us. Okay, there were only 3 developers. Maintaining a compiler and the associated software, and whenever we have to we have to release quote unquote a change, we were using floppy disks. This is like before the days of LAN, okay? There was no local area network. There's only floppy disks. So it was really awful because sometimes you cannot remember, did I put the right version of file onto the disk? So when the other person copies the source file, it may or may not be the one that you want to distribute, okay? And that can end up with a lot of problems. You can also know that the floppy disks are not exactly the most reliable media, right? So if you overwrite something, and the floppy disk decides to go bad, at the same time, then you lose, something, and usually can get a backup out of it, but it's not easy. All right. So are there any other questions about Git as a tool for revision control? It can do far more than just revision control, for project sharing and whatnot. But for this class, I recommend at least looking into it and see whether you can use it. In its simplest form, Git is pretty easy to use. You can just go to Google and just look for Git tutorial, and there'll be like tons of them. Okay, just go to YouTube and find Git tutorial. There will be tons of those. Ranging from a single person, single project, maybe even a single file, to multiple people working on a single project, and multiple people can work on the same file at the same time. So it's a really, really useful tool to look into. I would definitely look into it. All right, but that's not the main point of this class. The main point of this class is assembly code. Do we still have any additional questions about control structures before we move on to even more difficult stuff. Well, I wouldn't say difficult, but different. So control structures are fine, okay? Conditional statements, pre-checking loops, and post-checking loops. Those are the only three. And then we also have to learn how to translate, disjunction and conjunction into, break those things down into actual assembly code. We talked about that too. We're okay with that? Okay. So you'll be getting a new homework assignment on Thursday. No, I will not make it due next week, but the week after the break. Yes, go ahead. You had a question? No? Okay. All right. So this is all done. We are moving on to topic 6. Now, topic 6, I'm just highlighting it so that we know where we are. Topic 6 is interesting because when you write programs in C and C++, even in Java, this kind of stuff is never exposed to you. Okay, you just say printf or use the less than or greater than operator, and you have file I/O, right? File input output operations, and you're never aware of, hey, how does that get done? I mean, how can my program read from the keyboard, or how can it write to the screen? In this class, all this stuff gets exposed. The first topic we are going to talk about will be interrupts and system surfaces. Okay, this is a kind of difficult thing to explain without a platform to really, demonstrate the concepts, but I'll try my best. Okay. Section 2. I'm going to use my notes here, just as an outline to remind me what to talk about. You have to read the detail to find out, all the details about it. Okay, section 2 talks about life without interrupts. In other words, it's trying to explain why do we have a mechanism called interrupts in hardware. Okay, let's take the keyboard, as an example. Okay, so here's my typical keyboard. Nothing really fancy about it. And my computer, when I run the program, it wants to find out, whether I'm typing something or not. Okay, whether I'm pressing anything on the keyboard. How do you make that happen? Okay, forget you have an operating system and all kind of stuff like that. Just look at it from the simplistic point of view. How do you do something like that? How do I know whether a user is typing on the keyboard? Go ahead.
Sending a signal from keyboard to the processor. The processor captures the signal.
But what would the processor be doing when it's waiting for the user to input something? So we're going all the way back to the DOS days when you can only have one application running at any particular time. It's constantly scanning the keyboard, right? So the computer, the PC, is basically running in a tight loop, which looks like this. Hey keyboard, do you have an event to report? No? That's okay. Hey keyboard, do you have an event to report? No? That's okay. Hey keyboard, do you have an event to report? No? Okay, you get the idea, right? So it's a very tight loop, it's inquiring the keyboard continuously and say, do you have anything to report, okay? Because the keyboard has the internal ability to report, okay, there's a key press here, or there's a key release event. But nonetheless, the PC is still asking constantly and say, do we have a state change on the keyboard? Okay. That approach works well in DOS. When do you think we first encountered the limitation of this particular approach?
Processor's busy on doing something else and it's not detecting a key press at that time.
Right.
So if it's calculating, what's the square root of 10 billion, while it's busy doing that, a key is pressed and released. It just totally missed it.
All right. So in the history of PCs, when do you think this busy polling method runs out of gas, basically? When Windows comes along, okay? Okay, how many people know what DOS is, or what DOS was? Okay, several, okay, I think, as I continue to teach this class, the number of hands, will be lower, and there'll be fewer and fewer people who understand what is DOS, okay? But DOS is basically just a command line interface, and, really that's about it. When Windows came along, why do we call Windows Windows? It's a GUI, but there's a particular reason why it's called Windows and not DOS with a GUI.
Displays things within Windows.
Right, exactly. They're Windows, right? Each application runs its own space on the desktop called a window. And therefore it's called Windows because you can have multiple applications open at the same time. Okay? And even in Windows 3.1, I guess 3.1 may not be the case, but in Windows 95 for sure, you can have those applications running quote unquote at the same time. Okay? But that relies on cooperation. In other words, back in Windows 3.1, Windows 95, 98, and I think all the way up to Windows Millennium, it relies on the cooperation of the applications. In other words, let's say I'm opening Microsoft Word and Microsoft Excel at the same time, as two different windows, and Excel has some heavy-duty calculations to perform. But I can still type in Word, okay? Even though it's a little bit slower, I can still type and it will still be kind of responsive. And that's because these two applications are deciding to cooperate, out of their own, out of their own code, they decide to cooperate. In other words, Excel would do some calculations, and then when it comes to a certain point, it go, oh, maybe I should let somebody else have the processor. So it would yield control to the operating system. And then the operating system will figure out, okay, who else wants processing resources? If nobody else wants processing resources, it goes back to Excel, and then Excel can immediately get more processing resources and do more calculations. On the other hand, if Microsoft Word is open at the same time, it has the focus, and you're typing something, then the resource will go to the other application that also wants some, processing resources. Okay? What if there's a DOS window open? The DOS window decides and say, I don't want to give up control. I'm going to pull the keyboard, until this computer is turned off, right? And as a result, as soon as you open up a DOS prompt in the early Windows, not Windows 98, I think Windows 98 handled that fairly well, but in earlier Windows, if you open up DOS prompt, all the other windows become non-responsive because your DOS window still running, the DOS operating system wants to do the busy polling and is not giving up the control. Are we doing okay so far in terms of the explanation? And that's when life without interrupts runs out of gas. Okay, because when you can have multiple programs running at the same time, you cannot do busy polling anymore. Okay, it simply is not efficient anymore. What about a Linux server? Let's say the Power server. If Power Server is using the same approach of polling, to see if a particular command line interface has anything to do, it can only serve one particular CLI. You cannot have multiple people signing in and all trying to do different things at the same time. Okay, so that's the problem with polling. Section 3 talks about interrupts. Now, interrupts is not a new concept, not at all. Okay. By the time DOS came out, or CP/M came out, interrupts was already supported in hardware. It's just that it was never utilized in software. Why do you think people don't want to utilize interrupts?
Complicated.
It takes some extra work, okay? Now the extra work of interrupts is not really just changing the structure of the program, but also it comes with its own unique type of bugs compared to polling. Now polling, which doesn't have interrupts, if you have a problem, if you have a bug in the program, it's fairly reproducible. In other words, if you have a problem with the keyboard driver, there's a certain logic mistake that you make somewhere, it's really reproducible. Every time you do something, the same symptom will occur. On the other hand, with interrupts, when you have problems or bugs in your program, sometimes it may not show up for years. Other times it will show up every 5 seconds. And every time it shows up, the symptom can look completely different. Okay, so we'll talk about why that is the case, and that's the reason why I think people did not want to use interrupts, even though in hardware it is already there, but in software people just were not prepared to deal with interrupts. Okay, so to deal with interrupts on the processor side, there are several things. Let me just explain what it looks like first. Okay, so I'm just going back to this slide so it's not busy. The processor always has something to do. Okay, when it has nothing to do, it goes into a halt or sleep instruction on the regular PC. Why do you think the processor wants to execute a sleep or halt instruction when there's nothing else to do? Instead of a tight loop, jump to the same location, jump to the same location. To save power, exactly. Okay, by going into the sleep mode as much as possible, your processor is saving a lot of energy because it's not exercising the transistors as much. Okay, it's still exercising some transistors because there's still peripherals that are running, but the processor itself is really in a state where very minimal power is required. Okay. And also let's use the example of there's a heavy-duty program running in the background. Okay, somebody is trying to decrypt the encryption or decipher the encryption of something. Okay, so it's a really lengthy process. Interrupt means when I press a key on the keyboard, doesn't matter which one. Let's say the Shift key here. So I press the Shift key. The keyboard has the ability to detect a key press. Okay. The key press event is registered by the keyboard, and back in those older days, we have specialized connectors connecting a keyboard to the computer. It's a serial communication thing. I don't have to really explain the actual mechanism, but it suffices to say that the keyboard will basically tell the processor and say, hey, I need some attention. There's something that requires your attention. That's what the keyboard is telling the CPU. The CPU can then decide whether to process that interrupt or not. If the CPU says, okay, it's okay, I can process that interrupt at this point, then it will go into a subroutine to execute some code, in this case to process a key press or key release event. When it's all done, it will go back to continue executing whatever it was interrupted. Whatever was interrupted, you can go back and resume that operation. That's the concept of interrupts. Are we doing okay so far in the concept, with the interrupt concept? So on the processor side, we need several things. Okay, after you enable interrupts, the assertion of an interrupt pin, which is a physical pin on the processor, will cause a series of events on the processor side. In other words, one of the I/O devices, it doesn't matter which one, can be the keyboard, can be the hard drive controller, it doesn't matter. But somebody is asserting the interrupt pin, and it will cause the processor to do a whole bunch of stuff. The instruction in execution right at that moment will get to finish itself first. Okay? In other words, you cannot interrupt in the middle of the execution of one instruction. Interrupts can only occur between instructions, but cannot occur within a single instruction. So a single instruction, especially in this class, is what we call atomic with respect to interrupts. It cannot, interrupt the execution of one single instruction. As soon as the instruction is finished, the address of the following instruction is saved on the stack. In other words, there's a place in the system, in memory, that you can save the address. Okay, we'll call it a stack at this point. If you don't understand what a stack is, don't worry. We'll talk about it later on, throughout this semester. And then at that point, interrupt is disabled so that we cannot have stacked interrupts. When you are processing one single interrupt, you cannot have another interrupt to occur by default. Now you can always turn interrupt back on again in the process of processing one single interrupt, but that usually is not a good practice because you can end up with certain types of problems. And if a program needs to do something like that, something is really not right about the overall structure of the program. Okay, so the next step is the processor will look up a table. Okay, it's basically what we call a vector table. It looks up a table because each interrupt has its own entry in the table. It's called an interrupt vector. For a particular interrupt, there's a particular address to go to. So it's kind of like a jump table, or it's basically a jump table. The interrupt vector is an address to continue execution. In other words, the processor will look up the proper vector to go to depending on who is requesting the interrupt. Then we'll go to a particular address. The processor will continue execution at this address. This address, the location is the beginning of what we call an interrupt surface routine, or in short, it is called an ISR. An ISR, which is basically, it looks like a subroutine, except it is called, not in software, it's called quote unquote by hardware. Okay. Is that concept okay? In C and C++, you have subroutines. And in order for a subroutine to start execution, you have to call a subroutine. Is that okay, right? Okay. In the case of interrupts, it's just like calling a subroutine, except it is not triggered by anything in software. It is triggered by hardware events. Like, I press a key on the keyboard. There's a new packet coming in from the NIC, okay, from the network interface card. I move the mouse, okay? It triggers, the information sent from the mouse to the computer. So that's the triggering of the invocation of a subroutine, and that subroutine is called an ISR, which stands for an interrupt surface routine. An ISR typically is very short. It has to have enough code to clear the source of the interrupt. And during that, in the course of clearing the cause of an interrupt, the INT pin, the hardware pin, should be cleared. Okay, so let me explain what that really means. Okay, so let's say this is a keyboard event. Okay, I press a key on the keyboard asserts the interrupt pin to basically tell the processor, hey, I need some attention here. Okay, somebody press a key, you might want to process that. The processor will finish up whatever instruction it was executing when that happens. Okay, and between the execution of instructions, the processor will actually sample all the interrupt pins to try to find out, okay, who needs attention? And it will find out, oh, okay, keyboard, you need some attention. And depending on which interrupt pin is asserted, it will go to a particular entry in a table, and each entry corresponds to, quote unquote, a particular hardware. In this case, it will go to the entry corresponding to the keyboard. There's an address in the entry, and it will continue execution at that address. It's just like calling a subroutine, except in this case, it has to look up a table to find out where to continue execution. The subroutine to handle a keyboard event will read certain I/O registers, input-output locations, to find out what key was pressed. In the when that is done, when you're reading the I/O register to find out which key was pressed, that will trigger the keyboard controller to release the interrupt line, because the cause of the interrupt is no longer there. Okay, it has been processed. Okay, and then the interrupt surface routine will store the key code into some place and then trigger some other execution. When it's all done, okay, it will execute a special return instruction. The return instruction goes to the stack where we saved the address of the location that I was supposed to execute next before the interrupt. It will basically retrieve that location or retrieve that address, and then execution will resume at that location. So as far as what I was interrupting is concerned, it is as if the interrupt never happened. Because even though it was interrupted, when the ISR is done processing, it will continue execution where I was interrupting to begin with. And that's the cycle from the processor's perspective of what happens when an interrupt occurs. This is one thing that we cannot really experience when we're doing programming in Linux, because the Linux as an operating system is taking over control of all the I/O devices. So that means no interrupt is passed through to us whatsoever. And as a result, we cannot process interrupts. The closest thing we can do to interrupts is what we call a signal in programming. That was a concept that we used in cisp310, the systems programming class. But in this class, I'll see if I can just add some material to kind of introduce signal processing, because it kind of resembles what interrupt processing is, but it's not really exactly the same. It's not triggered by hardware. The only platform that I can use to demonstrate what an interrupt truly is is an embedded controller, like a Arduino, where there's no operating system operating below your program. Your program is the only thing running. There's no operating system. So in those cases, you can actually implement your own ISR and process hardware event the way you want it. But with that also comes great responsibility, because bugs in ISR can cause major problems. We'll describe some of those problems next time on Thursday. Thank you.
Real mode or real mode.